This is a short physics example video of impulse momentum with baseball. Here's the problem we're going to be looking at in this example. A 145-gram baseball is pitched to the batter so that it comes to the bat traveling horizontally at 40 meters per second. The bat exerts an average force of 9,000 newtons on the ball, lasting 0.7 milliseconds, and directed opposite and upwards slightly from the initial velocity of the ball at an angle of 23 degrees. What is the final velocity of the ball? So just to visualize this problem, the initial velocity of the ball is horizontal, and then the bat exerts some force on the ball, which I'm going to switch colors so we know it's a force, and the problem says that the force is directed opposite and upwards. And so I visualize that as looking something like this. It says a 23-degree angle upwards, slightly upwards. And so this is the force, average force. And we are asked to solve for V final. So we're not exactly sure what that's going to be. So I've duplicated my sketch of my setup, and now I'm going to fill in some of my other knowns. I know the mass of the baseball is 145 grams. That's 0.145 kilograms. It's important to convert the mass to kilograms if we're working with newtons, which has kilograms in it. I also know delta T, the amount of time, that's 0.7 milliseconds. Milliseconds is not the SI unit, so I'm going to convert that to 0.0007 seconds. Now, I know this is a two-dimensional problem. That's because these vectors, the velocity vector and the force vector, are not aligned. They're at an angle. And so I really need to break down all the vectors that I've been given into their component parts. So let's begin with the velocity. So my v initial, I can break down into v initial in the x direction, and that's actually the whole thing. Since it's directed horizontally, that's 40 meters per second. I happen to have drawn it going to the right, and so that's a positive number. My v initial in the y direction, just to be clear, that's a 0. The force is a vector too, and so it's going to break down into force in the x direction, and that should be equal to the total force, 9,000 newtons, times in the x direction, let's see, that's the adjacent side to the 23-degree angle, so that's times the cosine of 23 degrees. And then in the y direction, that's going to be 9,000 newtons times the sine of 23 degrees. And so if you put those into a calculator, the x component works out to be 8,285 newtons, rounding just a little bit. And the y component works out to be 3,517 newtons. Now, if it's directed opposite the velocity and the velocity was positive, this 8,285 newtons should be negative. But the upward number, the 3,517, that should be a positive value. So as the name of this video implies, this is a classical impulse momentum problem. So impulse, we use the letter J to stand for impulse. Impulse is equal to a change in momentum. Impulse is also equal to average force times delta T, the amount of time that the force acts on an object, and delta P is equal to the final momentum minus the initial momentum, We can actually expand that out even a little bit more. This is equal to mass times the final velocity minus mass times the initial velocity. All right, the problem asked us to find the final velocity, so here it is, finally showing up in our organization for our equations. Now, impulse and momentum are both vector quantities, and so we can actually break this up into a set of two equations. So force average acting in the x direction times time is going to be equal to the final momentum in the x direction minus the initial momentum in the x direction. And similarly, the average force in the y direction times time is going to be equal to the final momentum in the y direction minus the initial momentum in the y direction. So let's stick some numbers in. So starting out looking at my x components, the x component of my average force was 8,285 newtons times 0.7 milliseconds, which was 0.0007 seconds. And this had to be equal to the mass, which is 0.145 kilograms, times the final velocity in the x direction, which I don't know, that's what I'm solving for, minus that same mass, 0.145 kilograms, times the initial velocity in the x direction, which was 40 meters per second. If I put these in my calculator, I get that the impulse side, oh, and you know what I forgot? I forgot a negative sign. That's going to be kind of important. The impulse side here turns out to be a negative 5.80 newtons times seconds. And then over here on the momentum side, I still have my 0.145 kilograms times that final x component of velocity, and subtract off. This component here is really my initial momentum, the x component. Well, that turns out to be 5.80 kilograms meters per second. The units look different until you remember that newtons is actually kilograms meters times seconds squared. And so even though they're written differently, these units are the same, newton seconds and kilogram meters per second. Well, we have the same number here, negative 5.8, over here a negative 5.8. And so if I add 5.8 to each side, then I will discover that V final, the x component, has to be 0. So this ball doesn't travel horizontally at all when it leaves the bat, which is a little bit unexpected. So apparently this is like a foul ball. So now that we've discovered that this ball comes off the bat going straight up, let's figure out that velocity that it comes off the bat. So the y component of average force turned out to be 3,517 newtons times 0.0007 seconds. This is all going to be equal to the 0.145 kilogram mass of the ball times V final in the y direction, and then we subtract off the initial momentum of the ball in the y direction, which was 0, because the ball came in horizontally. So that's just saved us a little bit of math. When we solve the impulse side here, we're going to find that the impulse delivered by the bat was 2.46 Newton seconds. This is equal to 0.145 kilograms times that y component of final velocity. We divide both sides by 0.145 kilograms, and we will find that that final velocity is about 17 meters per second. So we have two components of final velocity. This was a 2D problem. We had to break it into two pieces. But one of the components has turned out to be 0. And so to get the total final velocity, it's actually, we don't have to do any Pythagorean theorem or find an angle. It's actually 17 meters per second upward. Oops, let me rewrite that. And we've solved the problem.